All right, yeah, it's all diced up. Go back up here. There we go. Okay, so I'm Chris. I'm going to be talking about Samza. I work at LinkedIn, and I'm an engineer here. So Samza is a stream processing system that we built and recently open sourced. We kind of do three kinds of data processing at LinkedIn. The first kind, which probably accounts for about 50% of what we do, involves online processing, and this is a request response RPC type system. And for that, we use a service-oriented architecture, Java stack that pretty much every other web company uses. On the other end of the spectrum, we do offline processing, and that ecosystem is primarily dominated by Hadoop. And that accounts for, I don't know, 25, 30% of our total processing. And the last chunk that we do is this sort of nearline processing or stream processing. And this is where Samza fits in. And this is the data processing that is asynchronous. It doesn't happen. There's not a user waiting for us to actually do the processing with a web page loading. But it happens shortly thereafter. So in the sort of 100 millisecond to a few seconds range, and then even beyond that to a few minutes range. That's kind of Samza's sweet spot. So there's a lot of use cases for this kind of stuff. We have things like newsfeed where we're handling updates, shares, social gestures. We have news where we're crawling the web, doing entity extraction, language detection, spam detection. We have ad relevance where we're essentially adding advertising to our inventory, and then we need to show it, update the rankings in real time. And things like email, where these are more reactive emails where you take an action or you come to the site after being dormant for a while and we want to immediately send an email to you. And then we also have this concept of these downstream data systems. These are things like search indexes or social graph systems or real-time OLAP systems where they're not holding primary data, but they're sort of feeding off of a real-time stream of data from our databases and updating their own indexes internally. So we have all these use cases. The ecosystem at LinkedIn is such that because of Kafka and another system we have called Databus, which actually is open sourced as well, we have almost all of our data flowing through some real-time system. So things like user activity get pumped into Kafka, shares, likes, when you change a company, all this stuff gets pumped in. We also have metrics and monitoring data, which is actually a really fascinating use case for doing SLA requirements and stuff. And the last one that I think is really unique for us is we have a pretty solid stream of database changes. And these ones are actually not in Kafka. These are in another system called Databus, which, like I said, is open source. But these two systems comprise sort of the bulk of the data that we have available to us. So like the next logical step is we want to start doing processing on this data. We want to do aggregation. We want to do filtering, transformation, updated downstream systems, and build products off of it, data-rich products. And so when we started doing that, this is several years ago, our initial approach was basically to build a web service but have a Kafka consumer or a Kafka producer in it, or a Databus consumer. And we found that actually this style of processing is much harder than you would expect. It's sort of deceptive in that way. There's a lot that has to be considered with respect to how you partition your data, how you manage your state in the case of failures. What happens if you get the same message twice? Most of these systems only give you that guarantee. How you join your data with outside systems, whether that's a service or another database, or what happens if your stream processor is behaving in sort of an unpredictable or non-deterministic fashion. So Samza is a system that's built to address a lot of those problems. When we looked around, this area is kind of interesting. It's been around for a long time as a research topic, and there are a lot of systems out there going back 15, 20 years, and none of them really, I would say, fully solve the problem. They take stabs at it from different angles. And so when you look at our LinkedIn ecosystem, we felt like there was space for us to sort of innovate and try a few new things to solve our own use cases and hopefully provide some benefit for some other people as well. So what I'm going to do now is kind of break down Samza into what it is and how it works sort of at a logical level. And then I'll talk a little bit about how that works with Yarn in the sort of physical deployment on a grid. So the most basic concept in Samza is really a stream. Since it is a stream processing system, a stream is comprised of messages, where a message could be anything from a user viewing a page to an event updated in a database. the concept of a stream in Samza is a little bit more heavyweight than you might think about in other stream processing systems. So if you look at things like S4 or Storm or Update or these other systems, they tend to be very lightweight and try to be very low latency on the way they handle streams. And as a result, it can make things challenging, like transactionality, for example. So Samza takes a reverse approach, which is we define streams as being partitioned, ordered within a partition, replicated, so we assume the partitions are going to be highly available, replayable, so you can go back in time, and they have an offset for each message, so you can sort of address messages independently. And the other thing I would call out here is just that the streams tend to be infinite, so that, like if you see here, partition 0 has a message 6. When you get to the end of that stream, it's not the case that you're done. You just begin waiting for more messages to get appended to this log. For people who are familiar with HDFS, the way to think about this is essentially as like a directory of sequence files where messages are getting appended and you're reading off of them. So from a consumer's perspective, you read messages from these partitions sort of at your discretion. So in this example, we have a consumer who's read partitions 0, messages 1 through 3, messages 1 and 2 of partition 1, and then the first 3 messages of partition 2. So what happens when a consumer then reads the next message is it picks one of the partitions to read from, in this case partition 2. It fetches the, the message for that offset, which is 4. Then it proceeds to fetch message 5 from partition 2, and so on. It might then switch to partition 0 and read that message. So the key here is that while ordering is defined strongly ordered within a single partition, between partitions the consumer has some control about which message it's going to be reading next. On the writer side, messages are simply appended to the end of a log. So the key thing to take away here is when you write a message, you need to determine what partition it's going to go into at that point. So for example, if a page view happens and you want to partition by member ID, you take that member ID and map it to a specific partition and then send the message to that partition. So how this relates to Samza is if you take a specific single partition, Samza allows users to write tasks that process the messages in this stream. And the way it does that is you define a task and you define the input stream, and then Samza will manage sort of the feeding of the messages into your task. And the way that looks is like this. So this example is essentially going to be reading page views from a topic or a stream or whatever you want to call it, and feeding them to your process. And in this process, it's going to be updating a counter for each page. So if somebody comes and views the home page, you would increment the counter for the home page. If somebody comes and views the jobs page, you would increment the counter for the jobs page. And then you're going to emit the count back out. So that you'll notice that the code implements a stream task. This is sort of the basic building block of a stream processor in Samza. The stream task has a single callback called process that gets invoked once for every message. The process method gives you the message that you're going to process. It also gives you a collector, which allows you to send messages back out, and a coordinator, which allows you to shut down the task if you want to or manage other task lifecycle. This should be pretty familiar or straightforward to anyone who's worked with anything like MapReduce. So in this example, we take the message, we convert it to a generic record, we pull out the page key from the event, we increment our counter. In this case, it might be the home page count, and then we send that count back out to a new stream called count stream. And this is partitioned by the page key, which means that every metric that you emit for a given home page key, for example, is going to go to the same partition. So going back to this initial example, a real concrete example would look something like this. You'd have a partition, you'd pull a message from it, and you feed it to the page view task, which then calls process, updates the counter, and sends the message to an output partition. And the process repeats itself. So again, this time you pull message 2 because your offset's been incremented because you processed the last message. You feed it through to your task again. And this time, the output message gets mapped to partition 0 because perhaps the page key was different. So what I've taken so far is essentially a view of just a single partition, right? But if you remember, the way I described Samza's view of a stream is it's actually multi-partition. And that's where a Samza job comes into play. A Samza job is essentially just a collection of the same task where each individual instance of that task is processing just one partition. So you can see in this example, we've got 3 partitions in the input stream, and you've got 3 tasks, one task processing each partition. I just want to emphasize each one of these tasks is actually the same code. It's just a different instance of the interface, essentially. One other thing to highlight here is just that it's not the case that you only can consume from one stream. You can consume from as many streams as you want. And when you do so, what you end up with is a case where you actually get the task that processes partition 0 processes partition 0 from all streams. And you might wonder why you would want to do that, but there's actually a really good use case for this. So if you consider, for example, a case where you want to compute advertisement click-through rate, you have two streams. You have one, which is your ad view stream, and then you have a second one, which is your ad click stream, right? And so you essentially want to join these two streams together and calculate the percentage of ad views that have clicks divided by the percentage of all ad views, or the count of all ad views, essentially. The way that works in this scenario is the ad views for partition 0 and the ad clicks for partition 0 get funneled to the same task, which allows that task to do this aggregation. If you don't have this partitioning concept, then you can't really do the aggregation that way. Now, this is just a single Samza job processing page views in our example. An actual data flow looks something more like this, which is kind of complicated. So to simplify things, I'm just going to eliminate the partitions. And what you end up with is a series of streams, each of which is fault-tolerant, replayable, and partitioned, and multi-subscriber, as this one shows. So you can see you have two jobs reading stream B. And this flow allows you to essentially send messages through what I guess most people would call a topology, but we don't call it topology. And the important thing to emphasize here is if you have a job 2 that you want to redeploy or take down temporarily, it's not the case that you need to be too concerned about upstream jobs that might be sending messages to it or downstream jobs that are reading from it. All that's going to happen is job 2 will cease to process messages. Anything that's in stream C or stream B is just going to continue getting produced and accrued on a Kafka broker or a database or whatever the stream is. And when the job 2 comes back up, all it's going to do is reprocess all the built-up data that's been stored in stream B and stream C until it catches back up to head. So now how does this fit in with Yarn is the big question. So if we go back to our job view, this kind of looks pretty familiar to people who have been dealing with MapReduce. What Samza does is it takes these tasks, which are processing partitions, and it groups them into containers. And a container is really just a Java process that handles one or more tasks. And in Samza's world, that basically means taking messages from the partitions, giving them to the tasks, and then taking the output and sending it back out to the stream. So if I eliminate the streams from this diagram, just to make life a little easier, these Java processes need to be run somewhere, right? And that's really where Yarn comes in. You end up with one or more hosts where you're going to be running these containers. And in Samza's case, right now, that involves the node manager, which is kicking these containers off and managing their lifecycle. We also have an AM. This Yarn AM behaves pretty much like most other AMs. It handles faults in cases where a container dies. It'll restart it. It handles partition management. So when a container is kicked off, it decides which of these tasks is going to run in each container. And it also handles things like some of the security-related stuff. The last sort of nuances here is where you would normally expect HDFS to fit in this stack. You will instead see our Kafka brokers. We co-locate our Kafka brokers right now with our node managers. And this allows for some data locality. It's sort of experimental, I would say, at this point. It seems to be working so far. But whereas offline processing tends to be a little more tolerant to performance degradation and issues with sort of co-location of processes, real-time and async processing tends to be a little less tolerant, so we want to be really careful about that stuff. And I'll go into a little more detail about process isolation later. But this diagram should look pretty familiar to anyone who's dealt with MapReduce, except instead of MapReduce containers and HDFS, we have Samza and Samza and Kafka. So if I go back and I compare the physical deployment I was just showing you with the logical layout that Samza sees things as, you can see that components all exist in the same spots. We have a container. The container is made up of stream processing tasks, which might be more than one task in a single container. And then we have streams, right? And in this case, the streams are held in Kafka. Or as I mentioned earlier, for some of our streams, we actually have this data bus system as well. One thing to highlight there is the fact that we do have more than one stream implementation. The way I kind of think about it is a lot like HDFS and Hadoop, where you can kind of think of Kafka as the first among equals in terms of implementations of stream systems, but we do support basically a pluggable interface like the file system interface that allows you to do other stream systems as well if you want to support those. So back to Yarn. The other two things I would highlight are, or I wanted to highlight rather, are sort of operational in nature. The first one is that because we have this sort of tighter sensitivity to performance, especially with disk, we have been experimenting with C groups to some degree and actually have gotten it running in a non-production environment for quite a long time, I'd say a few months, and it's worked pretty well overall. The C groups that we're using with Samza are basically just the vCore C groups. So we're using the memory enforcement that came with Yarn long ago that I think is just like catting proc meminfo at this point or something. We're using the C group CPU isolation, and disk and network are not being isolated right now, but disk is one we really, really care about because with Kafka, all the messages you're sending to go to disk. The other thing I wanted to highlight before Alan beats me is that I don't want to misrepresent the Samza clusters right now. The Samza clusters are running in their own Yarn grids. It's not the case that we're running in a multi-framework environment. So when Mohammed says we have a 40 node experimental cluster or a 100 node experimental cluster, those are sort of our Hadoop, Giraffe, MapReduce type environments. In Samza's case, we're running things a little differently. We have one Yarn grid in each of our data centers, and they tend to be a little smaller on the order of 18 nodes. And these grids just run Samza jobs. Part of the motivation for that is because we care a lot about latency with Kafka and Samza. Okay, so I already got the 5-minute notice, so that's the end of the talk, basically. I did want to highlight that we are currently incubating. We are looking for friends. We think we're friendly people. We have a demo that lets you get up and running in 5 minutes, so hopefully that won't be too hard or a barrier. And then once that's done, grab a newbie Jira, hop on IRC, hop on email. Happy to answer any questions. Looking for a lot of contribution if anyone's interested. So that's it. Yeah. It's a good question. So this is an open area of discussion we had. Initially when we built Samza, the setup looked a lot like Hadoop in that you basically had a single job. If you wanted to run something like a topology or a DAG, you ran multiple jobs. That works especially well with Samza because we have Kafka brokers in between that allow you to buffer output, so you can kind of bring a job up and down. Where we go with a higher level of topology, we haven't quite decided yet. One option would be something like Tez. Another option would be something like a script that runs multiple jobs. Since these jobs are infinitely running, it's kind of like a Hadoop workflow, but not quite. But the short answer right now is that we don't really have a concept of a topology of several jobs. We just have one global topology, which is all the jobs running on the cluster right now.
So even before Yarn, all of those jobs used to be deployed, not displayed.
Say again?
The jobs that you're running.
Uh-huh.
So they're all part of a single project.
Yeah. So the way Samza works is basically if you had something like you might consider a topology where you had 2 or 3 jobs, those all get rolled into a single package, and then you have one configuration for each job in that package, right? And so you run the same binary but with different configs, right?
And how many instances?
So it tends to be, by default, it's 1 container per job, and it really varies pretty drastically. So we have some.
So how do you handle scale, for example? Suddenly one of the jobs scales
more. Yeah, so right now you basically bump the config and deploy it with more containers, right? I used to have a demo, this really sweet demo where you could dynamically add more containers, and you would just press the plus button and you just keep getting more and more containers. Operationally, actually, it's a little bit debatable. Actually, it's very debatable as to whether that's a good thing or not when people start adding containers willy-nilly. So we opted for essentially config-based change, which requires you to do a full check-in. It has lineage, it has ACLs, you can verify who made the change. It's for an operational perspective, it's actually a lot better to do it that way. So Is that it?